Hi, welcome to a lecture on the effective aperture of large arrays. So first let me remind you where we're at. There are at least two ways to calculate the effective aperture of any antenna, and those two ways are as follows. First, you could figure out the effective length of the antenna, and from that get the effective aperture. And this is possible, but it's not entirely clear yet how to do this for an array. That is a topic for another lecture. The second method would be to figure out the directivity of the array, and then to use the relationship between effective aperture and directivity to compute the effective aperture. Now, the drawback of that approach is that directivity itself can be difficult to calculate. Remember, the formula for calculating directivity is to calculate the radiated field, then integrate over the field to get the beam solid angle, and then you can get directivity through the beam solid angle. So you might ask, short of a method to do this using the effective length, is there a better or simpler way? And the answer is that in general, no. But in certain special cases, including some important special cases, the answer is yes. So the point of this lecture is to explore simple methods for getting the effective aperture for large arrays in those special cases where a simple method exists. First, let me call out two bad ideas. And when I say bad ideas, I mean ideas that are tempting and sometimes used inappropriately, but which you should be aware of so that you don't make a similar mistake. Bad idea number one: find the effective aperture for one element of the array and then sum up the effective apertures. Well, the problem with this is that it ignores the array factor, which depends on the array geometry. And when you're simply summing up the effective apertures of elements, you are not considering the geometry. It turns out that only for certain geometries does the effective aperture of the array equal the sum of the effective aperture of the elements, and it's a pretty rare condition. Just as an example, recall that for a planar array of current moments, we came up with this result that shows the directivity in dBi on the vertical axis as a function of spacing between the elements in both directions. And we came up with curves for n equals 1, that is 1 element, 4 elements, 9 elements, that is 3 by 3, and then 100 elements, which is 10 by 10. And we found only in one case, that is, when the elements were half wavelength spaced, did we get that the total directivity was equal to the sum of the directivity of the elements. Now you might say there were other cases, other spacings, where we also saw that, but in those cases we had aliasing. So the only situation for this array where we had alias-free conditions, and also that the directivity was equal to the sum of the directivity of the elements, was for half wavelength spacing. In other words, for critical sampling. So in general, this idea doesn't work. In a few important special cases, it will work. Bad idea number two: maybe the effective aperture of the array is equal to the physical area of the array. And the thinking here is that, let's say you have a planar array and you stuff it full of elements. Maybe it turns out that the effective aperture of the array is the same as the physical aperture of the array. I applaud you if you think of this independently. It is a basis for doing some useful things, but in general, it's not going to work. The first problem is that we need to define what we mean by physical aperture. Is it simply the number of elements times the spacing between elements? Or do we need to account for margin at the edges of the array? This is not very precise. For a planar array, you can kind of imagine ways to define it, but they're arbitrary. And if you have other types of arrays, for example, distributed arrays where you just have random elements scattered around, now what does that mean? It's not really clear what or how you define that physical aperture. The second problem is you need to keep in mind that the effective aperture of each element might be quite different from the physical aperture of each element. For sure, when you just have dipoles, well, the physical aperture of a dipole is vanishingly small, and yet we know the effective aperture is significant. But even if you have something like a patch, it's not really clear how the area of the patch relates to the effective aperture of the patch. So there are some issues with this thinking. However, if we keep those two concerns in mind, we can kind of sort things out into three cases and possibly distill some useful ideas. So let's go ahead and do that. Case 1. Let's say we have a fully sampled array, and by that I mean spacings less than the critical spacing, but the aperture is electrically small. In other words, we don't have enough elements to make the physical aperture large compared to a square wavelength. Well, in that case, there's no shortcut to accurately estimating the directivity or the effective aperture. For electrically small arrays, it's hard to say anything about how the physical aperture relates to the effective aperture. Case 2. We are also fully sampled, but now we're electrically large. In other words, now we have enough elements that the physical aperture is greater than the order of magnitude of a square wavelength. So here we're talking about cases where the element spacing might be lambda by 2, and we have hundreds of elements so that the overall area is many, many wavelengths squared. Well, this is analogous to light through a window. We say this is approaching an optical condition. And what we mean by that is that the total power that we expect to intercept, that is, the total power that we believe the array can capture out of an instant electromagnetic wave, should be proportional to the instant power density, that's watts per square meter, times the physical aperture of the array. We think of this electrically large opening as capturing the instant power density, and the amount of power it captures is simply power density times the physical aperture. That's a simple physical idea, and the actual error in this approximation would come from the fact that there are edges here, and these edges interact with the incident ray, and that interaction would spoil this for a smaller array and would be less important for a bigger array. But let's continue with this idea. Since the received power, the captured power, is equal to the instant power density, which is copolarized, times the effective aperture, that's practically the definition of effective aperture, well, we compare these things. This compares to this, the power densities compare, so we're left with the conclusion that the effective aperture is at least approximately equal to the physical aperture. So in this case, in case 2, we believe that the effective aperture is well approximated as a physical aperture. You just have to remember, all the caveats that go into an effective aperture would also apply here. So here we're talking about the maximum effective aperture. It would be broadside incidence, conjugate matched elements, copolarized electric fields, and so on. And to the extent that those things are not true, this would be reduced. And the effective aperture would be less than the physical aperture. Furthermore, in the case of critical sampling, we would expect that this relationship does hold. The fact that the effective aperture per element can be summed up to give you the effective aperture of the array. But if the elements are not critically spaced, then we would expect the effective aperture to be not greater than that sum, and possibly less or much less. Case 3. Now we're electrically large as before, but we're undersampled. In other words, the spacings are greater than the critical spacing. So this would be like a distributed array, or an array of elements which are spread around in an ad hoc manner without attention to fully sampling an aperture or a volume. Well, clearly in that case, the effective aperture of the array is going to be less than the physical aperture of the array, if for no other reason that it's hard to define what the physical aperture is, and since it's undersampled, it's almost certainly going to be larger than the actual effective aperture. Now you could ask the question in this case, how would the effective aperture relate to the sum of the effective apertures of the elements? Well, to be honest, it could be greater than, approximately the same, or less than, depending on a bunch of other factors. So it's really difficult to say which of these is going to apply. But I'll tell you that from the above plot, the example we showed above, we see that although this case of the effective aperture being greater than the sum of the elements effective aperture, it will not be by much, right? If we go back up to this plot, we see that value of directivity for critical sampling is here, and it's kind of hard to get dramatically above that. So in the context of what we see here, this is not going to be by much. It's far more likely that we'll see something approximately equal to or something which is less than. So in conclusion, we say in case 3, it's pretty reasonable to assume the effective aperture will be less than, or at best, approximately equal to the sum of the effective apertures of the elements. Note that for electrically large planar arrays, and that includes cases 2 and 3 above, we have found that the effective aperture is at best comparable to the physical aperture, to the extent that a physical aperture can be defined, and maybe even likely to be less, maybe much less. So for such arrays whose effective aperture is less than the physical aperture, it's convenient to define a thing called aperture efficiency. And different authors give this quantity different symbols. I typically call it epsilon sub AP, aperture efficiency. And we define it as the effective aperture divided by the physical aperture. So if the effective aperture is equal to the physical aperture, then the aperture efficiency is 1 or 100%. But we would typically find the effective aperture is less than the physical aperture, in which case the effective aperture is going to be less than 1 or less than 100%. Said differently, an effective aperture close to 1 means we're making the best possible use of the available area. So it's a convenient design metric. In principle, it seems like it would be useful to maximize the aperture efficiency, to make the best possible use of the area occupied by the array. So let's summarize. In general, there is no shortcut to calculating the effective aperture or the directivity for an array. There are a number of important special cases, in particular for electrically large, fully sampled planar arrays, where it is possible to treat the array as an optical entity, as something which is able to capture power out of the air as a window captures light. And in that case, the available power is equal to the incident power density times the effective aperture, which is equal to the incident power density times the physical aperture. Now, sometimes people refer to this case as being the current sheet condition. That's a confusing term because the word current sheet gets applied in other problems and to describe other specific conditions as well. But here, when we're referring to the current sheet, we're saying that the array can be viewed as a continuous distribution of radiating current. So when this condition applies, we're saying that, even though the array is discrete elements in space, what we could really do is just view that as a continuous distribution of current. And whether we're sampling it in a discrete manner or just viewing it as a continuous distribution makes little difference in the actual patterns or effective apertures which result. When this condition applies, pattern calculation and pattern synthesis can be easily done doing Fourier transform techniques. Why? Because we've got a lot of intuition about how those continuous distributions work and how their Fourier transforms work. So once again, we find this relationship to be useful. The fact that the current distribution over an aperture is related to the pattern associated with that current distribution through the Fourier transform. That concludes this lecture on effective aperture of large arrays.